So, in this session we will look at this notion of NP completeness. So, this is a very important notion. There are major open problems related to this notion, and I'll start with. So, in the last towards the end of the last lecture we saw that there are several problems which we can solve in polynomial time, and I gave you some examples of problems where the best known algorithm we have take exponential time, right. So, we have, in your algorithms course you would have seen problems like sorting, shortest path, minimum spanning tree, network flows, and several in your problem sheets. And then we also looked at questions, algorithms for questions like is G bipartite, is the given graph connected, is it Eulerian. So, here are a bunch of problems for which we have seen, and there exist algorithms which are very efficient, linear, almost linear, m log n, n square, n cube kind of problems, algorithms. And I mentioned problems like minimum vertex cover and is the graph Hamiltonian. So, these are problems for which best known algorithms take exponential time. And I want to separate this with this for some reason, and here are problems for which so what we will look at today is to see more examples of these problems for which we have only exponential time algorithms, and we will see some relations between them. The relations between them, some connections between them is what is captured by this underlying notion of NP completeness. Okay, so let us see. So, we have already seen, let me define this or mention these three problems. Minimum vertex cover problem, where given a graph you want to find a subset of vertices that cover all edges and of minimum size. Okay. We saw that in certain class of problems, graphs, this is solvable in polynomial time. Which class of graphs? In bipartite graphs, you can solve it using Koenig's theorem, network flows, matching, and so you can solve it in polynomial time. But in general graphs, I said that we do not have a polynomial time algorithm yet, right. Let us talk about this problem, maximum independent set. So, what is an independent set in a graph? An independent set in a graph is a set of vertices in which no pair of them is adjacent. Okay. So, one is interested in given a graph, I want to find the maximum independent set, right. I mean, you can always find maximum or minimum, sometimes maximum makes sense, sometimes minimum makes sense. Minimum does not make sense in this case, right. Why? Just a single vertex is an independent set by itself. So, that is a minimum vertex independent set. So, here the interesting question, the optimization question is, given a graph, find a maximum independent set. A related problem is maximum clique in a graph, right. So, these are problems. I am going to write this as which I am going to use this notation VC for vertex cover, maximum independent set, and clique. These notations are for the problem. Given a graph, find a maximum click in the graph. What is a click in the graph? It's a subset of vertices where there is an edge between every pair of them. None of these three problems currently have a polynomial time algorithm. The best known algorithms are exponential time algorithms. What would be an exponential time algorithm for maximum click problem? And what do you check? Yeah, so try all subsets, take a subset of vertices and see whether there is an edge between every pair. And once you fix a subset, checking whether there is an edge between every pair of them is easy. You just go to your adjacency matrix and check they are all 1, right? And systematically enumerate, try all possible subsets as one clean brute force algorithm. There are slightly improved algorithms, but all of them take exponential time algorithms, right? Exponential time. So now what I want to say is that somehow these three problems are related in the following sense. If somebody gives me a polynomial time algorithm for any one of them, I will immediately get a polynomial time algorithm for all of them. Okay, this is the kind of connection between problems we want to explore. Okay, let's see why, right? This is actually very easy to see. So suppose there is a poly time algorithm. Let's call this algorithm A to solve maximum independent set problem, right? So somebody says I have a polynomial time algorithm, give me a graph, any graph. I have an algorithm which will run through in time some n cubed, n square, n power 4, n power 5 time. It will give me the maximum independent set in the graph. Okay. Can I use this algorithm to design a polynomial time algorithm for finding a maximum click in a graph? Not in the same graph, right? So you have to, we are not trying to find independent set click in the same graph. Just get out of that. We are talking about abstractly designing an algorithm for all graphs, right? So somebody gives me an algorithm A, which if you input a graph G, it will give you a maximum independent set. Okay, this is some black box which runs very fast. Now I want to use this algorithm A to design another algorithm for which should take as input a graph G and it should give me the maximum click in that graph. How can I do that? Does everyone see that? Right? Why? So what is the suggestion? You want to design an algorithm for click using the algorithm A for maximum independent set. So what is my algorithm? New algorithm A prime. Let's call this algorithm A prime. What does it take? It takes an input G in which I want to find a maximum click in the graph, right? So what do? Complement the graph, right? How do you find the complement? I'm going to write this G complement. How do you complement the graph? Right. And how fast can I find the complement of a graph? Given an adjacency matrix, what do? Wherever there is a 1, change it to 0. Right? That's all. That's an n square algorithm. Run through your adjacency matrix. So this will take n square time. And then what do? I feed this complement graph to my A and say A will only give me maximum independent set. So I will say, okay, give me a maximum independent set in this graph, which is a complement graph. And if it gives me whatever, some S subset of in whatever input graph, right? And that set is the maximum click in the graph, in my original graph, right? So output S. And why is this the correct algorithm? Because a set of vertices is a click in my graph if and only if it is an independent set in the complement graph, right? If there is, because that's exactly the way complement is defined, right? So that's it. So how much time? So now I have let's call this entire algorithm, which will so this algorithm takes as input G and then it will output S. So input, so this is my algorithm A prime, which will take my graph G and it will output S. And this whole algorithm is an algorithm for the max click problem. And it is using an algorithm for independent set as a subroutine, right. So, I will take some graph where I want to find the click, I do some surgery to that graph. In this case, it is just a complement, and then I feed it to my algorithm, which will give me the max independent set, and it gives me a max click, right. So, overall, how much time does the algorithm take? N square plus whatever algorithm A takes, whatever time A takes, then I assume that A takes polynomial time. So, overall, I have a polynomial time algorithm for click problem. Okay. So, in there is a notation for it, which is that I am going to write this as click that is that if you can solve maximum independent set. So, click is easier in some sense than independent set, because if you have an algorithm for independent set, I have an algorithm for click. Okay. This what I have done is what is called a reduction. This is not new, we have seen this, where have you seen this? We have used network flows to solve a maximum collection of edge disjoint paths, right. Here you have a graph in which you want to find a maximum collection of edge disjoint paths, you want to design an algorithm for it. What did we do? Okay, maximum collection of edge disjoint paths between S and T. So, we take that graph and feed it to my network flow algorithm. Well, my network flow algorithm needs capacities. So, I added capacity 1 for every edge. I fed it to my network flow algorithm. From the output, I know the answer. So, this is, using subroutines is something we always do in any, in your programming anyway. So, that is what it is. Now, notice that the converse also is true here, right, because if I have an algorithm for the click problem, you can use it to solve the independent set problem in a very similar way. I take the complement. So, this is also true. So, these two problems are polynomially related. If you have a polynomial time algorithm for one, you have a polynomial time algorithm for the other. Let us look at the vertex cover problem. Okay, that requires a little bit more work. So, again, let us play the same game. Suppose we have an algorithm A for maximum independence set. Now, I want to know, can I use it to find a minimum vertex cover in a graph? Okay. Now, to understand this, let us try and see some relation between minimum vertex cover and maximum independence set, right. So, suppose S is a vertex cover in a graph. Okay, so here is my graph. I need to draw some picture sometime at least. So, okay, give me a vertex cover for this graph. Two, 4, 7. Is 2, 4, 7 a vertex cover? Yes, no? No. Okay, why not? Because 1, 5 edge is not covered. Okay. 2, 6, 1. 4, 5 edge is not covered. And 3, 5, 7. Okay. Is it a vertex cover? Looks like. You can run through every edge and check. What are the remaining vertices? 2 and 6, right? 2, 4, 6. Can you see some property of the remaining vertices? Okay. So, let me ask my question again, answer that. You are there almost. Okay. I asked, let us take the complement set, which is 2, 4, 6. What is the property of this 2, 4, 6 set? It is an independent set. Can we prove it? In this example, it is independent. Can we show that it is always independent set? If you have a vertex cover, see, this is very important, right? Difference between example general algorithm, proving, these are all important. If I give you a vertex cover and look at the set complement of the vertex cover, it so happens that here it's an independent set. Can we somehow show that it is always an independent set? I mean, if it's an independent set, you won't have an edge there. Okay. So, more precisely, take a pair of vertices in the complement of a vertex cover, right? So, here's the proof, right? Take the complement of the vertex cover, pick a pair of vertices, suppose that edge is, there is an edge. Who is covering that edge? S is supposed to cover every edge in the graph, right? So, how can the complement have an edge in the graph, right? So, here is a theorem, important theorem, you can prove it, that if S is a vertex cover, then V minus S is an independent set. The proof is because if there is an edge in that V minus S, then it contradicts the assumption that S is a vertex cover, because S is supposed to cover every edge. Okay, so now let us go back here. Suppose I have an algorithm for finding a maximum independent set. Can I use it to design an algorithm for minimum vertex cover? How do I do it? So, give me an algorithm for minimum vertex cover, independent set. They must form a vertex cover because of this theorem, because this is also true. If you have an independent set, the complement is a vertex cover, right? And so, if basically what is my algorithm? If you have an algorithm which takes my graph A and gives me an independent set, max independent set, I will take the complement, set complement here is minimum vertex cover. So, if I want a minimum vertex cover, run your max independent set algorithm, look at its output, take the complement set, that is a minimum vertex cover, right. Why is it a minimum? It is a vertex cover. Why is it a minimum vertex cover? Well, if there is a smaller vertex cover, then this is not a max independent set. The complement set will be even larger. It contradicts the fact that, so all these statements, you know, they are subtle, require a line proof. Okay. So, this is it. So, what have you shown? If you have an algorithm for, so vertex cover we have shown is less than or equal. So, if you have an algorithm for maximum independent set, I can use it to solve my minimum vertex cover, and in the same way, if you have an algorithm for minimum vertex cover, I can use it to solve maximum independent set. So, that means we do not know the status of these three problems about whether they have a polynomial time algorithm or not, but they all go, you know, all of them have a polynomial time algorithm or none of them have a polynomial time algorithm. So, they all go in triples. Okay. So, now let me, so this is the kind of relationship we want to understand between problems, you know, how are these kind of problems, how can we use an algorithm for one problem to solve another problem, and define this, get this notion of NP completeness, right, that is the goal. So, let us get into some formal notions. So, P, I am going to define this class of problems solvable by an algorithm in time polynomial in the input size. Now, there are many terms here. If I have to define some formal notion, I have to say what is a problem, what is an algorithm, right, what is input size, right. This is theory. I am going to build some nice theory now. So, but do not worry, I am not going to do those formalism now. Okay. It is enough more or less with whatever informal understanding we have with that. And also, for some technical reason, I am going to focus on decision problems. What are decision problems? These are problems for which the answer is yes or no. So, find the max flow in the network is not a decision problem. Is the graph bipartite? Is a decision problem, because is the graph Hamiltonian? Is the graph Eulerian, right? Is the input sorted? These are all decision problems where the answer is yes or no. So, find the minimum vertex cover is not a decision problem, but it is not a serious restriction because I can turn around. I mean, typically, we are interested in optimization problem. We are interested in minimum vertex cover, but suppose I have an algorithm for a decision version of the following problem, which is that given a graph, is there a vertex cover of size k? Okay, this is a decision problem because the answer is yes or no. Now, suppose you say I have an algorithm which will solve in polynomial time this following decision problem, is there a vertex cover of size k for any k? Can I use it to solve my optimization problem? Because my goal is to find the minimum vertex cover. So, how can I use the algorithm for a decision version to solve my optimization version? That is it, right. So, keep querying the algorithm for different values of k. So, I ask, is there a vertex cover of size 1? Algorithm will say yes or no, because this algorithm is supposed to answer the decision version of the question. If it says no, I ask, is there a vertex cover of size 2? So, I do some n queries to the algorithm, some polynomial number of queries to this decision version, I can solve the optimization version. Okay. So, this is not a serious restriction, but for the development of this theory, we need this decision version problems for which the answer is yes or no. So, that is what we are going to look at. Right? Okay. So, what are some examples of decision problems for which we know? Okay. So, let me, even though I said I am not going to get into formal notions, but let me actually tell you what it is for people who are interested to dig deeper. So, since it is a decision problem, you can define my input into two parts, the parts for which the answer is yes, the parts for which the answer is no, right. So, what is my input? Input, for example, could be the set of all graphs. Let us say the problem I am interested in is the graph bipartite. Okay. So, I have my language, so set of all inputs. And let us say y is the set of all inputs for which the answer is yes. Then what is my problem? Given x in L, is it in Y? Think of L as a set of all graphs and Y is the set of all bipartite graphs, right. So, problem I am interested in. So, this is all related to the problem. The problem I am interested in is given a graph, is it bipartite, right. Think of L as a set of all graphs and Y is a set of all bipartite graphs. Then what is my problem? Given an x in the language, what is the x in the language? It is a graph. Given a graph, is it in Y? That is my question. So, you can formally define all of it. That is all I wanted to tell you, that there is a formal way of doing all this. So, now what is an algorithm? A Turing machine. Okay, a deterministic Turing machine which will take my x in the language and answer in polynomial time, run through polynomial time, whether it belongs to the set y or not. Okay, this y, L, everything depends on the problem I am interested in. So, if I am talking about graphs, L will be the set of all graphs. I may be talking about formulas, L may be the set of all formulas. I may be talking about some strings, L will be the set of all strings and so on. So, problem, algorithm, okay, input size is something important. Okay, what is, because we are talking about sometimes if you change the way you encode the input, polynomial could become exponential, exponential could become polynomial, so it is important. So, by input size, so there is this, so when I say L and set of all inputs, these are actually some encodings of the input. And let us say we encode it in binary. Okay, I will give you an example where it is important. So, we encode entire input in some binary. So, if you are giving me a matrix adjacency graph, it will be an adjacency matrix. If you are giving me a sorted, a list of numbers, I will write each number in binary separated by some symbol which is also translated in binary, and that is my encoding of the input. So, the size of the input is that length of that input instance. Okay. Now, I will give you an example. Okay. So, let us just stop here and understand, is the class of P clear now? It is a set of all decision problems. By problems, you can think of it as the way we have been seeing, or you can think of this formal notion, for which there is some algorithm which will run in time polynomial in the input size and gives the answer, correct answer. That is what P means, right. We have seen examples, bipartite, Eulerian, connected, is the graph a tree, is the input sorted, right. These are the kind. Is there a path of length at most 5 between S and T? Okay, given a graph and S and T, so it is a decision problem, right. I have to translate everything as an yes or no question. So, let us look at this following problem. Okay. So, we know, so let us say G, S, T, K, and I ask the question, the question here is, does there exist an ST path of length at most K? This is a decision problem because the answer is yes or no, as simple as that. A problem is decision problem, the answer is yes or no. Is it in polynomial time solvable? Is there a polynomial time algorithm for this? It is an unweighted, undirected graph. Okay. Let us make life simple, undirected, unweighted. What do I do? Breadth first search starting where? That is it, right. Do a breadth first search starting at S and see that at level K or even below T is there. So, this is a polynomial time algorithm, this is a linear time algorithm. So, this is in the class of all polynomial time solvable problems, right. We saw a lot of examples and this is it. So, I will just give you an example for this input encoding, how it matters, right, because that will complete my picture of P. Okay. So, let us look at the following problem, right. Very simple problem, given an integer n, is it prime? Okay. Given an integer n, is the number prime? Can you give me a simple algorithm for this? You know what a prime number is. Okay. So, what would be a simple algorithm for this? Okay. So, not 1 from 2 to, okay, because by definition, yeah. So, for I going from 2 to n by 2, if I divides n, return false or something, and if you come out successfully without returning, then you will return true. Right? Why is it enough to go only up to n by 2? By definition, you should go up to n minus 1 really, right, because a number is prime if there is no divisor other than 1 and n, or you can even go up to square root of n. Okay. Everything needs a proof, right, correctness. You know, for your competitive programming, maybe you do not need a proof, but well, you need it because algorithm may be wrong on certain instances. So, he says yes, you can go only up to square root of n, and the argument is that if a number is not prime, it must have a divisor within square root of n. Why? Because is it possible that all its divisors are greater than square root of n? Because even if it has one divisor, it has two divisors, right. If x is a divisor, n by x is also a divisor. It must have at least two divisors, and if both the divisors are greater than square root of n, how can the product be equal to n, right. So, if there is a divisor for the number, you should catch it before square root of n. Good. So, here is a nice algorithm. What is the complexity of the algorithm? How much time does it take? Assuming division takes some constant time, then it is just a square root of n algorithm, right? Polynomial time? Even better than linear, right? We have not even seen, oh, well, we've seen something like binary search maybe. Okay. So, this looks like a polynomial time algorithm, but it is not. Why? Let us look at the size of an encoding of n. What is the size of a binary encoding of n? If I write n in binary, how many bits do I use? Log n. Okay. So, my input size is not n, my input size is log n, right. So, input size so, what is square root of n, which is the complex runtime of the algorithm? It is actually 2 power half log n. Okay. This is just the definition of log n. What is 2 power half log n? 2 power log n is n. 2 power log n is n, because definition of log n means that how many times you have to take divide by 2 to get something 1. So, 2 power log n is n and you take square root. So, 2 power half log n. So, it is this term which is my input. So, this is like 2 power n by 2. If n is my input size, then this is an exponential algorithm. Capital N is my input size, then this algorithm which I told you is an exponential algorithm. Okay. And the reason why you want a why you define the size is important. So, suppose I have a 20 digit number and I want to check whether it is prime. I want the algorithm to take polynomial in 20, not polynomial in the input value. Input value could be very huge, right. So, the size of the input is the size of a compact encoding, right. Now, somebody should be asking me, suddenly you are bringing this binary thing. We have been seeing graph algorithm, n vertices, m edges and all that. You never mentioned this binary encoding there. We have been happily saying it is an n square algorithm, n cubed algorithm, mn algorithm, where n and m are actually the number of nodes. So, what is the answer? So, let us say if I have a graph on n vertices and m edges, what is the size of the encoding? How do you represent the graph? How do we represent the graph normally? Let us say we use adjacency matrix. What is the size? N square. It is not log n, right. N is a number of vertices, but that is not the input really in those graph problem, because there is so much, the encoding and the adjacency, everything takes n square bits. So, the input size there is n square, or if you use an adjacency list, then it will be like n log m or something like that. If you are trying to do sorting n numbers, n is not the input, this n numbers are the input. So, the input size would be at least n, something more than n. Whereas, here just the n integer is the input. So, encoding log n bits is sufficient. Okay. So, so it is important to know that what is the unary encoding, binary encoding, what is the input size is important. So, let me just go back to my definition of P. It is all decision problems solvable by an algorithm in time, polynomial in input size. Okay.